Break time is what?
3:30.
3:30. All right.
If there is break time, 15 minutes, and then class will be 5.
5, okay.
So you go and have lunch or something. And then come back in 6.
Okay. Hello. Hi. So good evening, or good afternoon, maybe. So my last name pronunciation Hsu, Hsu. Okay. So just a brief introduction, and I'm not trying to be a disappointer, or doesn't need a. Okay. Anyway. Okay, I can use this. Okay, all right. So doesn't mean I like to be professional students. My original purpose is trying to get the Ph.D. in nuclear engineering, because that's my main interest. Because the school I attend, that was #1 in the world, nuclear engineering. But then, after I passed prelim, that was after Apollo landing, industry very bad. My colleague from nuclear engineering cannot find job because nuclear power plant, 60% of the hiring is mechanical engineering. The real nuclear probably only 10%. So my professor said, well, if you don't want to continue PhD, at least you get an MS. Then you can exit. So that's why I got an MS. And transfer back to mechanical aerospace, get a PhD. That's the reason. Okay. And I have my professional engineer many years ago, in the 80s. So that was a long time ago. Okay, so I work a long time in the industry, in all those different areas, mechanical, aerospace, nuclear. My earlier career is in nuclear engineering. Then the last 10 years at Boeing, I kind of transferred to system engineering because the government and the aerospace industry, defense industry, emphasize very much on systems engineering. So I was the pioneer for the Boeing, and also could be the pioneer in the world to revitalize the system engineering. System engineering is old subject, but being forgotten. That's why it's called revitalized. So my main career is at the Boeing company. Okay. Right now I'm just full-time teaching mainly at the Cal State in Long Beach, but also teaching at the UCI. I'm also board member for their systems engineering certification programs. Because my system engineering reputation, so that's why European people like UK hiring me as a visiting professor 7 years, and also I also went to Netherlands, also teach system engineering, and later also in China. And in AIA, I've been teaching system engineering in the past since 1992. So I don't even know how to count, many years. Okay. So I'm a fellow because of my contribution in system engineering area. Also the editor-in-chief for their professional progressive books in the system engineering area. I'm also active in INCOSE stands for International Council on System Engineering. And the ESEP is a very highest level, you can call certification, but this is like grandfather clause. It's excellent system engineering professionals. I'm also active in their working groups and so on. Even today, I'm still active for the both societies. Okay, so that's basically, that's me. And this is the contact number, and two email address. If you like, you can send email to me or call me on my cell phone. So with that, I'm going to start the lecture. That's one, right? So maybe I need to click here too, right? Or doesn't matter, I can use here, right? I don't see here, but that's okay.
Yeah, it's just that.
Okay. All right. So.
You remember how to write?
Yeah, I know. Where's the pen?
Yeah.
Oh, here is the pen, yeah. The FE sample question and also diagnostic question I will reserve to the last period of the course. So I start the lecture now, okay? So starting from 13, I guess, it's chapter 13 or section 13 from NCES. So properties of substances. And because there are too many pages, and also we need to go over the diagnostic questions and also the FE sample questions. So I'm going to be brief in presentation, but you can stop me anytime you have a question, okay, if not enough for you. So start with properties. So pure substance, best way to explain maybe from this curve here. From this one here, which I may draw one. So this the TV diagram here, and this one is the dome, right? So you want to enlarge it?
Oh, no. He says that he wants you to use the pen to write so we can see your drawing.
Oh, okay. So this
That is the pen.
I have pen.
It is selected.
Yeah.
Just write stuff.
Okay, this is the temperature coordinates. This is the volume coordinates. Okay. I'll change to red. Okay. Color is
right here. This one.
okay. So it's the temperature versus volume coordinates, and the dome here. The curve, under the curve we call dome, D-O-M-E, like a church. So inside the dome is two phases, liquid and vapor. Okay, so this line is the saturated liquid line. Okay, and this curve line is the saturated vapor line. So between saturated liquid and saturated vapor, and we could have volume here or volume here. We could have volume here. Any point between the saturated liquid and the saturated vapor. So later on we'll get a quality to determine the volume here. But right now I'm just focused on the faces here. On this side of the dome, this liquid is sometimes called subcooled liquid or compressed liquid. Okay, and inside is mixture between liquid and vapor. Of course, here near the saturated vapor, that has more vapor. Near the saturated liquid line, there's more liquid. Okay, depending on where it is, right? So on the right hand side of the dome curve, it's superheated steam. Okay, so that quickly kind of expand saturated vapor line and superheated vapor and the previous page on the subcool, right? Yeah, subcool liquid, okay. Okay, so I used the analogy, which I'm jumping ahead a little bit, but we're going to cover this later. Inside the dome in Europe, it's called church. So inside the church, man and woman married. Outside church, not married. My analogy is between this are constant pressure line. This is constant pressure line. We have many constant pressure line. Okay, many. Okay, so this constant pressure line, once inside the dome, the pressure and temperature fixed relationship. If you know temperature, you know the pressure. You know the pressure, you know the temperature. Because you can see the temperature inside is not increased. Because when the water heat to say 100 degree, continuous heat, temperature not increase. That heat is used to convert liquid gradually to vapor. The vapors then until saturated vapor. So that's why temperature is constant inside. Also the pressure. Different pressure have different corresponding temperatures. So inside here, I call the mirrored region between temperature and pressure. Okay. So this another curve is called molar diagram. It's pressure and enthalpy. No, this is not the molar diagram. This is pressure versus enthalpy. Okay, but there's another. I'm sorry, this pressure versus enthalpy here. But usually we use volume. But this diagram uses pressure enthalpy. I don't know why. Usually we use. Is this a volume or enthalpy? I cannot tell. It should be. It is enthalpy. Okay. Usually we use volume here. So this curve, different from this one, is. This is temperature versus volume, so constant pressure going this way. So if this either pressure against enthalpy or pressure against volume, the constant temperature line now comes this way. Okay, this is another one too, right? So again, you can see inside the dome, temperature is constant with fixed pressure, so still married. It's just a different coordinate system. One is the temperature, this one is pressure. But inside the dome, pressure, temperature have fixed relationship. I'm going to jump through this part because I don't think we'll have questions, not many questions in this area. So I'm going to jump to state function now. Mass, pretty much, probably you already know, right? Either kilogram, gram, or pound. That's U.S. customer system. Pressure, again, we have a U.S. customer units and also metric units. The highlight will be so this is 1 atmosphere pressure. But 1 atmosphere in the U.S. customers system is 14.7 psia. In the metric system, it's 101.3 kilopascal. That's the main pressure units you should know, right? Pay attention. Okay. And temperature, there are two different scales.